Welcome everybody to another video. Linear algebra is sometimes described as the only part of mathematics where we can actually find solutions to problems. That is, where we can actually solve equations and write explicitly solutions to them. This is not entirely true. But it is very often the case that when there is a problem in a advanced mathematics, and if we can reduce the problem to a problem in linear algebra, then we usually can reap very big benefits from that. In fact, linear algebra is of tremendous help in studying field extensions, and you will see this in the next video, how I'm going to use the linear algebra to make a key observation that will actually allow us to solve a lot of problems involving these field extensions, and in particular will eventually allow us to answer some of these questions that I asked at the beginning of the semester regarding constructible numbers. So there are only a few notions I will need from linear algebra, which means this is just going to be a very short introduction / review of the concepts you already know. What's with the premium edition? That's because the definitions of vector spaces that you have learned in previous linear algebra courses are limited, or were limited, by the fact that the only fields you really were familiar with were the real numbers and the complex numbers. Well, in fact, we were also familiar with the rationals, but for some reason, vector spaces that involve rationals as scalars are not part of standard curriculum. So today we're going to give a definition of a vector space that works over any field, and you will see that the definition is actually almost identical to the ones, to the definition over the reals or over the complex numbers, the ones that you're very used to. So the main difference for us in our definitions would be that we are going to work over an arbitrary field. So this is part of a definition that you never actually saw in the definition of a vector space, where somebody writes, let F be a field. So for us to define vector space, we will need a field and we will need a set of vectors that will be our vector space. So definition: a vector space V over F is a set together with two operations. Now this should look quite familiar now, because definition of a field and of a ring also involved two operations, addition and multiplication. Here, there will be some other two operations. In fact, one of them is something very similar to the ones to the operations in the rings and fields, namely addition. But the other one is somewhat different. So what are the two operations? One. So maybe I just this one. Addition of vectors, which means, i.e., if V1 and V2 are in V, then we define V1 plus V2, the sum of these vectors. That's another element of V. And the other operation is called scalar multiplication. This is somewhat different from the operations we saw over rings and fields, where we always took two elements of a ring, or two elements of a field, or in the case of addition of vectors, two vectors, and we got a third element of the ring, a field, or a vector. Here, the two elements that we will take come from different things. One of them will be a vector. The other one will be an element of the field F. So, alpha, I'm not even going to write anything between these two symbols, alpha V. So, maybe, i.e., if alpha is in F and V is in V, then we define alpha V, and that's another element of V. Okay, so what's a scalar multiplication? I take an element of the field and a vector, and I define a new vector. So scalar multiplication is something that eats an element of a field, a vector, and spits out a vector. So you of course know scalar multiplication from standard linear algebra, which is over the real numbers, or over the complex numbers. There's actually nothing standard about it. It's just that that's probably what you learned. So there you would take a real number and a vector, and the real number would multiply the vector to give you another vector. And you call that scalar multiplication. So the only difference here so far is that the scalar can come from any field. It does not have to be the real numbers. It could be a rational. It could be an element of the field Q adjoin radical 2, Q adjoin cube root of 2. It could be a complex number. It could even be an element. It could even be a congruence class modulo a prime number. You know the congruence class is modulo a prime number from a field. Okay. And there's the whole laundry list of boring axioms that this thing needs to satisfy. I'm going to write them for completeness here, but they are just the same axioms you know from linear algebra that you learned. So just for the sake of completeness, let's write them all down. One, there's associativity of addition. For all V1, V2, V3, and V. 2, there is commutativity of addition. 3, there's the existence of the zero vector. Okay, and just call this V0, such that V0 plus V is equal to V. For all V and V, we call V0 the zero vector and write simply 0. Now some people would put an arrow on top of it. I could do this, but and as you've already noticed in abstract algebra, a lot of things are actually done by understanding from the concept from the context what the notation means. So when you see a vector, we're talking about the vectors, and I write 0. You should know that this is the zero vector, not, for example, the 0 in the field F. 4. For every V in V, there exists another vector which I write negative V, such that when I add these, I get the zero vector. That's of course the additive inverse. So far, as you see, all these 4 axioms do not involve anything that refers to the field F. Okay, now the rest of the axioms, 5 through 8, will actually talk about the connection between the elements of F and the vectors. So I have the following. So alpha beta v is alpha beta v for all alpha and beta in F, v in V. Oh, so this has to be read correctly, right? What I'm doing here is beta times V. Beta is an element of F, and this is a vector. So beta times V is another vector. And then I multiply by another element of F, so by another scalar, and I get another vector. And the thing is that the axiom 5 says that you could have done it the other way. You could have actually multiplied these two scalars, and this multiplication here, that's not scalar multiplication, that's multiplication of elements in F. So that's just multiplication in the field F. And this together then gives me another element of F. And this other element of F times this vector, so this is now scalar multiplication here, right? So let's maybe just write this here so that you see. So this is multiplication in F, while this is scalar multiplication. Okay, what's more? You know that fields have identity, so I want the identity in F to just not do anything to the vectors for all v in V. 7 alpha v plus v1 plus v2 is equal to alpha v1 plus alpha v2 for all alpha in F, v1, v2 in V. So in other words, you have the distributive law of scalar multiplication. And lastly, you have the distributive law, and again, but with respect to the field elements. Okay, so that's just a definition of a vector space over any field. Again, if you put F equal to R, you recover the definition of a vector space from other linear algebra courses that you took. But you could take F to be anything. And let's now define some of the important concepts. Oh, actually, let's define some other concepts here, and then we'll do examples where we apply all these concepts. Okay, so another definition. Let F be a field, and let V be a vector space over F. Remember, that just means that the scalars come from F. A subset W of V is called linearly independent if alpha 1 v1 plus alpha 2 v2 plus ... alpha n vn, giving you the zero vector, for some v1 through vn in W, and alpha 1 through alpha n in F, implies that all these scalars must be zero. In other words, it is not possible, if you have a linearly independent subset, it is not possible to find any non-zero linear combination of these elements that gives you zero. That's the identical definition from the one you know already from linear algebra. The only difference is again that the scalars, the alphas, come from F, from that field that we fixed. So same assumptions. Let F be a field. Let V be a vector space. Over F. A subset W inside V is said to span V if for every element V in V, for every vector, you can find vectors v1 through vn in W and scalars alpha 1 through alpha n in F, such that V can be written as alpha 1 v1 plus alpha 2 v2 plus alpha n vn. So a vector, a subset is called a spanning set if every vector in the vector space can be written as a linear combination of elements of that subset W. And finally, so same conditions, F a field, W a vector space. A subset W of V that is both linearly independent and spans V is called a basis. If V has a basis that consists of finitely many elements, then we say that V is finite dimensional. And in fact, it's a theorem that in a finite dimensional vector space, any two bases have the same number of elements. This number is called the dimension. Of V over F, denoted dim F of V. Okay, I'm not going to prove this theorem. This is a standard theorem in linear algebra. In fact, you do not have to assume finite dimensionality. This theorem is then still true, but that would require us to talk about cardinality of infinite sets, which is not really relevant to us here. So we'll only be concerned with finite dimensional vector spaces. So let's now give a few examples. And not only examples that you might have already seen in linear algebra, but I want to also focus on examples which might be new to you in this new context where the field is allowed to be anything. In particular, it could be something else than the real numbers. Okay, but let's start with a standard example over the real numbers so that you remember, so that you can connect these notions that we develop here with the ones that you already know. So R2 is a two-dimensional vector space over R. How do I write elements of R2? I'm going to write them as column vectors. So R2 consists of column vectors x, y, where x and y are real numbers. Okay, and then I add them coordinate-wise, and of course scalar multiplication is just the scalar multiplies both of these coordinates. And we can also draw a picture. For this, you know that R2 can be just represented as a plane. So this would be the x-axis and this would be the y-axis. So let me give examples of spanning sets, linearly independent sets, and so on. So if I take the following set, 1, 0, 0, 1, and 2, 3. This is a spanning set. So I claim that any vector inside R2 can be written as an R-linear combination of these vectors. So why is that? Well, because if I take any vector, let's say I take any vector, so x comma y, so xy, I can just write it as x, which is a scalar. Remember, that's an element of R, times 1, 0, plus y times 0, 1. So anything can be written using these vectors. So in particular, so for example, if I want to write a minus 2, 3, I can just write minus 2 times 1, 0, plus 3 times 0, 1. If I want to write so for example, 4, 6, I could write it as 4 times 1, 0, plus 6 times 0, 1, but I could also write it as 2 times 2, 3. So in a sense, a spanning set is a set that has enough vectors in it so that every vector can be expressed as a linear combination of these vectors. However, if you just would like to say, okay, but it doesn't seem like I would never need this vector 2, 3 to write any vector on the plane, you're right. You actually can just do with 0, 1 and 1, 0 to write every vector on the plane. It looks like this set just has too many vectors. And a precise way of saying that it has too many vectors for the purpose of writing any vector on the plane is to say that the elements of the set are actually not linearly independent. So this is not linearly independent. Why? Because I can write a linear combination of these vectors if you're trying to show that something is linearly dependent, so not linearly independent, you want to take these vectors and just stick in some scalars here where not all of them would be 0, and try to get 0. So look, I can just use minus 2 plus 3, minus 3 plus 1. Yeah, if you try that, that gives you minus 2, 0. That gives you 0 minus 3 plus 2, 3 is 0. So this shows that they are not linearly independent. But if I throw out one of these vectors, if I just do 1, 0, 0, 1, this still spans because we just showed it here, right? In this sort of orange calculation that all you need is these two vectors to span. But now I claim this is actually linearly independent. That is, you can try this exercise for yourself first. Can I find now scalars to make these two add up to 0? And you see there's no way to find any, right? Because if I chose just any alpha and any beta, this addition here will give me vector alpha beta and for this vector alpha beta to be 0, you need to have alpha equal to 0 and beta equal to 0. So this implies, remember this 0 really is the 0 vector, right? It looks like this. Same here. So this implies that alpha and beta must be 0. So this set is linearly independent. So a basis. Okay? So as a consequence of this, you get that the dimension over R of R2 is 2. Okay, let me stop here, and in the second part we'll do more examples.